In this video, we're going to talk about simple harmonic motion. Simple harmonic motion. For that, we need to analyze first the motion of an object attached to a spring. Let's say that I have a block with mass m that is attached to a spring mass m, and the spring is basically displaced from equilibrium. Spring displaced from x equals to 0 equilibrium point by x. All right, so you can see that here it is displaced from equilibrium by an amount x. So this is my x-axis. And when we do this, if the coefficient of kinetic friction between the surface and the block is 0, there's only going to be one force this block will feel. The block will feel a restoring force. Okay, so I have no friction. Therefore, the net force on the x-axis is what I call the restoring force, Fs. Okay, and how much is this force? This force is proportional to the displacement and opposite in direction. It is given as minus kx, where k is the spring constant. So k is the spring constant, and the force is minus kx. This is known as Hooke's law. So as a result of that, if I write Newton's second law for this block, Newton's second law says the net force acting on an object is equal to its mass times acceleration when viewed from an inertial reference frame. So the net force acting on it is minus kx, and this is equal to its mass times its acceleration. And acceleration by definition is dv dt, and that is second derivative of position with respect to time. So remember, we replace d dt with a dot here, so we can say that this force, the net force, is equal to kx is equal to mx double dot. So the double dot means it's the second derivative, second derivative of the position with respect to time. Okay, I'm going to call this ratio k over m omega square. So I can rewrite this equation as x double dot is equal to minus k over m times x, and let's substitute for k over m omega squared, and the reason why I'm doing this will be clear in a moment. Then we have x double dot is equal to minus omega square x. So this is the equation of motion. Equation of motion. So if we analyze any mechanical problem where we obtain this sort of equation of motion, we're going to say that the system exhibits simple harmonic motion. So systems whose equation of motion whose equations of motion are in the form x double dot is equal to minus omega square x, are set to exhibit simple harmonic motion. Simple harmonic motion. SHM. So there are many systems that exhibit simple harmonic motion. For example, you can think of the atoms in a crystal. The atoms will oscillate around their equilibrium positions, just like a block of mass m is attached to an oscillating string. So knowing the solution of this mass spring system is basically the key to understanding many other physical phenomena that involve the same type of equation of motion. Okay, so that we know this equation, what is the solution to this equation of motion? We can say a solution to equation of motion is of the form x of t is equal to a cosine omega t plus phi. So basically I'm suggesting that this is the function that satisfies, function of time that satisfies this differential equation. Now, since you don't know yet how to solve differential equations, basically we can just suggest a solution and then we can check if it does satisfy the differential equation. So if I take one derivative, x dot, that is dx dt, I will get minus a omega sine omega t plus phi. And if I take another derivative, x double dot, second derivative with respect to time, I will get minus a omega square cosine omega t plus phi. Now notice that this is minus omega square times a cosine omega t plus phi, and this is basically x. So I find that x double dot is equal to minus omega square x. So this equation, this function satisfies the differential equation. Okay, now the elements of this solution, a, it's an oscillating function, it's a cosine function. A is the amplitude of the oscillation. Omega is the angular frequency of the oscillation. Phi is what is known as initial phase or phase constant, and omega t plus phi is the phase of the motion. So A, the amplitude of the oscillations, it's measured in meters. Omega is the angular frequency, that is in radians per second. Phi is the phase constant or initial phase, that's measured in radians, and omega t plus phi is the phase of the motion. That's also an angle, so this will be measured in radians. And remember, how did I get this omega? I called omega square as k over m, so omega is square root k over m for the spring mass system. So I have to keep this in mind. Okay, now if this is a periodic oscillation, so it's an oscillating function cosine omega t plus phi, as you can see in the figure here, this block is going to keep oscillating around its equilibrium point because there is no friction, there is no energy dissipation mechanism, so this will be a persistent oscillation. So what is the period of this oscillation? Well, as a concept, what is period? The period t, it's defined as the time required for the particle to go through one full cycle of its motion. So it is measured in seconds. It's the time interval for one full oscillation cycle. Okay, so how can I calculate the period? Well, I look at the phase of the motion. So how much of an change in the angle does it take for cosine to repeat itself? Cosine function is cosine periodic with 2 pi, an angle change by 2 pi. So I find that if I look at the phase of the motion at a time t plus a period and compare it with the phase of the motion at time t, if the difference is equal to 2 pi, then I will have introduced an angle change of 2 pi to cosine function. This will give me omega times the period is equal to 2 pi. In other words, the period of oscillation is 2 pi divided by omega. So that will be the time it takes for the particle to complete one full cycle of its motion. Or this block of mass m to complete one full cycle of its motion. The inverse of the period, is called frequency. Frequency f, it's measured in hertz. 1 over hertz is 1 over second. And what does it physically mean? If you have a clock and you wait for 1 second starting at a certain point in time, you count the number of full cycles. That is going to give you the frequency of the oscillation. For example, I stay at x equals to 0 at time t is equal to 0. I see that this mass goes to its maximum, comes to its minimum, and goes to its maximum again in 1 second. I basically conclude that it has completed one cycle in 1 second. The frequency is 1 hertz. If it completes 10 cycles in 1 second, the frequency is 10 hertz. Okay, so frequency is equal to 1 over the period. It is omega divided by 2 pi, or we can say omega is 2 pi divided by the period, or 2 pi times the frequency. And since I know omega, I can say that the period is 2 pi divided by square root k over m. So it is 2 pi square root m over k is the period, or frequency is 1 over 2 pi square root k over m. So I have this relationship between frequency, the angular frequency, and the period. So there are different ways of writing this relationship. Now going back to my position as a function of time, x of t, my solution to the equation of motion, a cosine omega t plus phi. If I calculate the velocity as a function of time, that's going to be minus a omega sine omega t plus phi. If I calculate the acceleration as a function of time, one more derivative, minus a omega square cosine omega t plus phi. So this is x dot, this is x double dot, or v dot, if you wish. So that's basically telling me the maximum speed the particle can have is a omega. The maximum acceleration the particle can have is a omega squared for this motion, which means it is a square root k over m and a k over m for the maximum acceleration. So I know position is a function of time, velocity is a function of time, acceleration is a function of time. That gives me the complete information about kinematics, and I know the maximum values of the velocity and position of this particle that performs the simple harmonic motion. Now let's assume an initial condition here. At t is equal to 0, the particle is at its maximum point, A, amplitude. Okay? So if I substitute this to my equation of the position, x of t is a cosine omega t plus phi, so a x at 0 is a cosine phi is 0. So how is that possible? No, so a cosine phi is a. So how is that possible? That means the initial phase is 0 radians. Okay, so I start with a 0 radians initial phase, and when I plot a cosine omega t plus phi, where phi is 0, so it becomes a cosine omega t. Basically, I see that it starts from a maximum here, as you can see, and then it goes through a minimum minus a, and then it goes to its maximum again and keeps oscillating following this function. The amplitude of the oscillation is a. The time it takes to go from the initial position to amplitude to the next maximum position, amplitude, it's going to be one period. So x initial, I'm assuming, is a here. So it's an oscillation between plus a and minus a. So this is an oscillation between plus a and minus a. Now, if I look at the corresponding velocity as a function of time, velocity as a function of time was minus a omega sine omega t plus phi, with phi is equal to 0. Velocity as a function of time is minus a omega sine omega t. So at t is equal to 0, what is the velocity? It's going to be equal to 0 meters per second. So my oscillation in the velocity starts from 0, and then as time goes by, I go to more negative values. So I reach minus maximum velocity. Then the velocity keeps oscillating following the sine function. So I reach a maximum velocity here and here. And what is that maximum velocity? I can write here, it's going to be a omega and minus a omega is the maximum velocity. And if I go to acceleration, acceleration as a function of time is minus a omega squared cosine omega t plus phi, with phi equals to 0. This is going to become, acceleration as a function of time is minus a omega squared cosine omega t. And what is the acceleration at t is equal to 0? It's going to be equal to minus a omega squared, which is minus a max. So this is going to oscillate between minus a omega squared and plus a omega squared. Okay, so it's oscillating with the cosine function, and it will basically follow the cosine function. All right, so it will follow the cosine function. Now, what I would like you to observe here is that when x is equal to x max, the amplitude, the corresponding value of velocity is 0. The corresponding value of acceleration is minus a max. So I look at this relationship here. I find that if I compare these values at the beginning, I have positive a max, x max, 0, and minus a max. And on the other hand, if you look at what happens at x is equal to 0, so let's look at x is equal to 0. Then what is the value of the velocity here? Velocity is minus v max, or the speed is maximum. The acceleration, on the other hand, is 0. That makes sense because if you go back to Hooke's law, it's telling you that the force is proportional to the displacement. When the displacement is 0, force is 0, and due to Newton's second law, the acceleration should be 0 when x is equal to 0. So what we find is that there is a phase difference between position and velocity, and position and acceleration, also between velocity and acceleration. So for position and velocity, the phase difference is pi over 2, and for position and acceleration, the phase difference is pi. So you can see that here I start with x equals to a, and then I wait for half a period to reach x is equal to minus a. Then in full period I go to x is equal to a. So the full period t corresponds to a phase difference of 2 pi. Half a period corresponds to a phase difference of pi. So you can see that half a period time difference between maximum and plus maximum and minus maximum, the acceleration starts from minus maximum and goes to plus maximum. So it's basically following this part of the position. So that means I have a phase difference of pi, and between the position and the velocity, I see that the position reaches 0 in a time interval t over 4. T over 4 corresponds to a phase difference of pi over 2. So after a phase difference of pi over 2, if you ignore basically this part of the position, you can see that this plot is the same as the velocity oscillation. So I have this pi over 2 phase difference between them. Okay, now there's one more thing I'd like to mention. So these plots have been produced by the assumption that at t is equal to 0, x is equal to a. So let me think about another case here. Now at t is equal to 0, I'm going to say that the particle is at its equilibrium position, So if that's the case, then I will write x of 0 is equal to a cosine 0. This has to be 0. So what does that imply? It's going to be a cosine phi is equal to 0 at t is equal to 0. And what does that imply for phi? Phi is either plus or minus pi over 2. Well, there are many values phi can take, but within one full cycle, I have plus or minus pi over 2. Now, if I also tell you that at t is equal to 0, the particle is moving to the right. If at t is equal to 0, the particle is moving to the right, that is to say, the sign of the velocity is positive. So it's going to be a positive velocity moving to the right. So if I look at velocity at time t is equal to 0, minus a omega sine phi, I want this to be positive. So I have two candidates. Phi is pi over 2 or minus pi over 2. So phi should be minus pi over 2. So that sine of minus pi over 2 is minus 1. I will get velocity at t is equal to 0, a omega, which is a positive quantity. So you can see that you need two types of information here, both the sign of the velocity and the position, to determine what the initial phase should be. And if it has an initial velocity a omega, that's equal to the initial velocity vi, so the amplitude of the oscillation is its initial velocity divided by omega, the magnitude of the velocity divided by omega, and I conclude that x of t should be vi over omega cosine of omega t plus phi, but I just found phi is minus pi over 2, so it's going to be vi over omega